Okay, I hope the system is working. Hello everybody, welcome. Hi. Hello. Can you guys hear me? Is the sound working? Okay, I hope the system is working. Hello, everybody. Welcome to our YouTube show. I'm Po-Shen Loh, and I'm normally a math professor at Carnegie Mellon University. But right now, as you can see, this is not quite Carnegie Mellon University. I'm actually joining you from Harvard because that's where I happen to be today. But today we're going to be talking about something quite different. I'm very happy that we're doing this official collaboration again with Math Kangaroo USA. Those questions are really, really nifty. And you've heard me say this before, but I'm going to say it again because sometimes the people joining this live solve are new. Actually, when I first looked at their questions, I thought, wow, there are such interesting questions that you can ask that don't require you to know a huge amount of different math facts or formulas, but really see how creative you are. Well, we're also very pleased, since this is an official collaboration, to have a special guest today. And she actually represents Math Kangaroo. Her name is Ying Yang, and she's an assistant professor at University of Washington, Bothell. She normally works on marketing. Actually, she works on thinking about the motivations of salespeople. But she's also the co-director of Washington State's Math Kangaroo program, which is how we got to know each other. Actually, after last year's state awards ceremony in Seattle area, we filmed a little Q&A together. You can actually watch it online. We'll send you a link off of this YouTube comment section, I think. But more about Ying. Ying's also really passionate about helping youth find passion in learning and also helping support adults. With that, I'm going to turn this over to Ying to say a few words. Ying, it's all yours.
Thank you, Po-Shen. It's really my pleasure to be with our partner again. As a Washington State co-director of Math Kangaroo, we were so glad that you were with us to honor our kids who really love math from our Math Kangaroo questions. So just briefly message about Math Kangaroo. Math Kangaroo USA is a national nonprofit organization with the mission of helping all the kids to love math. For the past 26 years, we have been organizing all different kind of national, international math Olympiad competition for thousands of students from the students ranging from K to 12. So our focus is on improving students' math scores, but also teaching them new strategies for solving word and logical problems, helping them to get critical thinking skills up, and also gaining confidence in the classroom and also in their lives. Other than the academic excellence, I also want to encourage the students to consider participating in our Math Kangaroo competitions in March next year. We do that annually. For participation in the competition, you will get prizes like this, toys. If you get really well, you will get recognition. You'll get prizes like this, recognition like this, and some toys like this. I think it's going to be fun working with our problems and then also gain prizes. Okay, thank you for giving the time for us, and it's all yours, Luke.
Well, thanks, Ying. Thank you so much for saying those comments. We always are very, very happy to work together with Math Kangaroo and all of you. Well, the rest of this live solve, I personally won't be answering the questions. It's a little bit difficult for me to do that standing outside in the cold, but we have some incredible people who are going to lead this. We've had the pleasure of working with them. They're live instructors. And in case you've noticed, our live instructors are people who are both brilliant at math, and they've also learned a lot about how to perform, but fundamentally, they're just really nice people. And today, you'll have Luke and Shelley, and they'll introduce each other. So I'll turn it over to them. Luke, why don't you take it away? Luke, you can go first, and have a great live solve. See you guys.
Yeah, thank you so much, Professor Lowe. All right, so our teachers for today is me and Shelly, and I'm going to introduce Shelly today. So Shelly Yang is a very qualified individual. She represented Nevada at Math Counts Nationals and was the state champion in Math League. She's also an Amy qualifier and the co-president of her school's math club. Outside of math, she loves video production, piano, and teaching. So that's really cool, Shelly.
Thank you so much, Luke. And I'm here with Luke, who's also super awesome. In fact, Luke is a two-time Amy qualifier and even an AMC8 perfect scorer. So he's super great at math. And in addition to that, in 2022, he represented Michigan at the National Math Counts competition. And so he also started and currently coaches a Math Counts team of homeschool students who qualified for the state competition. And aside from math, he still somehow has the time to enjoy guitar, theater, basketball, cooking, spending time with friends and family. So awesome, awesome person all around.
Yeah, all right. So without further ado now, we're going to hop into the problems. So problem 1. Alina folds the image below along the dashed line, and then it shows an image. And if you guys can't see the dashed line, I'll like, kind of draw it out for you guys here. It kind of goes around here. And the question is, which of the following squares fold into the identical one? All right, so let's just kind of go through the answer choices to solve this problem. So if we look at the first answer choice A, there's a bunch of different squares that have this particular pattern. And I'll just circle some of them for you guys. There's one right here. There's one over here. There's one over here. And there's one over here. There's one over here. There's one over here. There's one over here. And there's one over here. If you kind of look at this dashed line pattern, though, I don't see that any of these fold onto each other, right? Because this square would go, the bottom left square would go somewhere over in the top right, but it wouldn't precisely go where we want it to, which would be somewhere up there. And these two also don't go to each other because this square right here would fold to a little bit closer than this square up here. Going to the next number, the 0, obviously this would not work either because folding this square over would not make the perfect match because there's in fact just one of those. Going to the next two, this also wouldn't work because both of these squares are below the dashed line, so that's not going to work. Going to the next square, this also doesn't work because this square goes a little bit below this square right here. All right, now let's move on to the next answer choice, B. You can kind of circle some of these squares, but once you start to realize is that this square right here and this square right here do in fact fold onto each other. So I think this is going to be our match, which is really, really cool. So B is going to be our final answer, and don't mind that I circled A. B is the final answer. All right, let's check if we got it correct. Yes, the answer is B. All right, Shelly, what is about the next problem?
All right, awesome. Before we go on to the next problem, I just wanted to comment on this a little bit. So I really like this one just because it's not immediately obvious what's going on. Like it's really difficult to visualize like what's going on in this question, but I really like how there's also kind of like a systematic way of going it, just as Luke showed. So awesome, awesome. Okay. And I do see some of you guys in the chat, they're kind of popping up here. So essentially what's going on is in the Zoom, you might have seen someone called Chat Relay. That's one of the accounts that are also joined from the Zoom. So in order to have your message come up here, make sure that you are private messaging Chat Relay. So if you open up the chat box, it might be, I don't know who it would default to, but make sure that you've selected Chat Relay as the person that you're sending these messages to. And as these people have done already, your message will show up here and everyone else can see it, which is super cool. You guys can exchange your ideas there. Hello, yes, I'm seeing some more messages in the chat. Awesome. Ooh, the problem is a little blurry. Okay, good that we have that feedback. Thank you, guys. All right, let's make this a bit bigger. Cool. So let's hop on to the next question. Yeah, please let us know if you guys can't hear anything or if stuff is blurry. Okay. Is it still blurry? Okay. Let's see. Let me see if I can make this a little bigger. Okay. Right. Hopefully that's a little better. Okay, cool. So we have question number 3. We'll just be going through the odd problems today. So number 3 says that Sasha created secret symbols for the English alphabet. He writes basil as shown in figure 1 and red as shown in figure 2. So how does he write the word bread? Okay, well, let's see. So we have some options here. Let's see if we can get an even bigger diagram. Awesome. So we've got a slightly larger diagram here. Okay, Let's make this a bit bigger since it seems like there's still some trouble. Okay, cool. So let's take a look at the diagrams that we have here. So in our first diagram, believe that was the word basil. Okay, so it looks like each of these slots represents a letter. So this target symbol looks like it's going to be our first letter. This little U looking thing looks like our second letter, and it's essentially like symbols that are replacing letters. So our first word is basil. So B matches with this first character. We have A matching up with this U character, U looking thing, and then S-I-L. Okay, and our next word was red, so that's figure 2. So figure 2 is going to be R-E-D. So we're trying to look for which of these symbols matches up with the word bread. And as with any language, it's nice to know what the symbol B would translate to, or what symbol B would translate to. So we look at our options here. Seems like a lot of you are saying C, so let's see if that's what it is. So our only letter here that represents B looks like this one, and that seems to match with this target symbol. So let's look at which of our options have the target as the first symbol. So it doesn't look like this one that has the U. Doesn't look like this one either. It kind of looks like a target, but not quite the same. And it seems like a lot of you are saying C. Well, this does begin with a target symbol, so that's already a good sign. But let's check our other options first. So this one also doesn't start with a target. This one doesn't start with that target symbol. So it looks like this one is the only one that matches that first letter B. So we can safely say that our option's going to be C. And of course, we have to check our answer. So drum roll. All right, hooray. It looks like it's C. Cool. All right, Luke, can take the next one.
Yeah, really, really good solution, Shelly. All right, let's look at the next problem. Dina sets up 3 bricks on the floor behind a wall. From the front, the bricks look like the figure on the right. What do the bricks look like from the back? All right, this is very, very interesting. So the first thing I notice is that the wall right here is kind of in front of everything else, right? So when we look at it from the back, the wall is going to be behind everything else because it's in front of everything else right here. So this D right here is not going to work because we want the wall to be in the back and not the front. And in D, the wall is going to be in the front. So that's not going to work. All right. The next thing I notice is that this brick right here is behind the brick in front of it. And that brick in front of it is the long and skinny one right there. Sorry if all of the circles are a little bit confusing. But that means that when we have these 2 bricks, this group of 2 bricks over here, and we can circle this in all of the different pictures, we're going to want the gray brick to be behind the front brick because, no, sorry, I meant that the other way. The long and skinny one is going to be behind the other one. So that means that B and E are our only 2 choices left. And the reason why this is because these 2 bricks have the exact same configuration that they did over here, and that's not what we want. So we can cross out A and C. And now it's just between B and E. All right. So there's very, very little difference between these 2 pictures, actually, from what we can see. And the only difference is that in E, this brick over here and this brick over here are exactly the same height. And in the picture B over here, this brick is a little bit shorter than this brick. And when we look at the picture, through all the little circles I made, it might be a little bit confusing, but I believe that this brick is a little bit shorter than this brick. So B is going to be our final answer, and we can also cross off E as well. All right, let's check our answer. And the answer is indeed B. So good job, everybody. All right, Shelly, what about the next problem?
All right, awesome. Okay, this is another really cool problem. Thank you, Luke, for that one. All right, let's take a look at number 7. Okay, wow, this is a long one. Okay, that's a lot of reading. Hopefully that's not too blurry, although let us know if it is. Okay, so looks like with number 7, there are two concentric wheels, each marked with 7 positions. Oh, okay, it looks like it is a little blurry, so let me make this bigger. Okay, let's see. Cool. So right here, there are two concentric wheels. That basically means they both have the same center, and they are each marked with 7 positions. The wheels spin in opposite directions, and each makes a complete turn in 7 minutes. At the end of each minute, each letter lies exactly in front of a number. The picture shows the first 2 positions of the wheels, and we can see that initially, letter A is in front of number 1. So let me hide chat for a second so we can see these diagrams. So right here, A is in front of 1, and B is in front of 2, and so on and so forth. And the wheels turn until letter C is in front of number 2. So we want to know which number is letter F in front of that point. Okay, so this one's a little bit tricky because we have to kind of visualize how the wheels are going to turn in respect to each other. So let's see, even though A starts in front of 1, that's going to change as we go on, right? Right here, we see that A is in front of 6 now, B is in front of 7, so on and so forth. But there's one thing. Oh, you guys can't see the diagram. Okay, let me make the diagram bigger since we've read the problem. Okay, so, right. So with these diagrams, we can't exactly tell like when each letter lines up with what number, but one thing we can be sure of is the order of the letters and numbers are preserved. Ooh, let's see. Oh, this is a nicer diagram. Okay, cool. So let's make this one bigger instead. So yeah, as I was saying, the order of the letters and numbers are never going to change. That is, B is always going to be to the right of A, C, D, E, F, G, and the same thing with 1 to 7. So 1, 2, 3, 4, 5, 6, 7. This one also has 1, 2, 3, 4, 5, 6, 7 in that order. So that is never going to change. So actually, if we fix C in a position that is in front of 2, then we know all of the other letters, all of the other numbers are going to follow in that fixed order. So, okay, let me draw a new diagram since it seems like, let's see. Okay, so let's draw the inner circle first. So we have A, B, C, D, E, F, G. Let me know if these are more clear here, because I know this part of it is maybe a little bit thin. Okay, awesome. All right, so let's take a look over here. So we have A all the way to G, and we want it such that C is in front of 2. Let me check. Yes, C is in front of 2. So that means the 2 must be in front right here. Okay, well, we know that once we have a 2, 3, 4, 5, 6, 7 are going to follow it in clockwise order. So that means 3 is going to be right here. So 3, oh, that's not showing up. Okay. Let me change that really quick. Okay, so that means 3 is going to follow right here. 4, 5, 6, 7. Actually, I think I skipped one. 6, 7. Ah, yes, I skipped 1. So it's going to look something like this. So C is in front of 2, D is in front of 3, E is in front of 4, and then F is in front of 5. And that's exactly what we were trying to look for. What was in front of F? And so looks like the number that's in front of F is going to be 5, which let me show the chat again. Seems like that's what some of you are saying. So let's take a look at our answer. Is it going to be 5? And it is. So awesome job, everyone. That was super cool. All right, I'll pass it over to Luke now.
All right, we have a very, very interesting next problem here. And the problem is Peter has a package weighing 445 grams and the following 8 weights. And it has 500, 200, 200, 100, 50, 220s, and a 5. He puts the package on a scale as shown. What is the smallest number of weights he needs to balance the scale? All right, so the first thing I'm going to point out here is that it seems as if you can only, or maybe some people, including myself, would initially think that you can only put weights on the left side of the scale, but you can also put them on the right side of the scale. So that's just something to keep in mind. And all right. So let's just try some things out to start out. All right. So let's say that we have nothing on the left side. Let's say we put nothing on the right side and we just have this 445 over here. So we're going to try and balance that 445 with only putting packages on the left side. So we could do a 200, a 200, and then we would want to do two 20s and a 5, and that would be 5 total packages. But this seems very, very random, right? And there doesn't seem to be a lot of process to this. And we also got a pretty high number, right? We got 5, and the highest answer choice is 6. So this doesn't seem as if it's going to be right because we didn't necessarily have a process for how to do this. And we also assumed that there would be nothing on the right-hand side, which is not necessarily going to be true. So let's take a different strategy. What happens if we went over on the left-hand side and we said the right-hand side would also just have some packages that would balance out what we had on the left-hand side? So let's say we have 500 on the left-hand side. And then we had a 445 over here. So we need 55 more grams over here. And we can actually make that really easily with a 50-gram package over here and also a 5-gram package over here. So that's going to be 3 total packages. So that doesn't necessarily seem very convincing to me, if you ask me, though. How do we know we can't get this with 2 packages precisely? So let's think about that for a second. If we had 2 packages precisely, we would want either one of them to be on the left-hand side, right? Or one of them to be on the right-hand side. So we would want the package on the left-hand side minus the package on the right-hand side to equal exactly 445. And that's not going to work because the package on the left-hand side would have to be 500 because nothing else is greater than 445. And then this package would need to be 55, which would never work. Then one other case is if we have 2 packages on the left-hand side. And this also wouldn't work because every one of these numbers is divisible by 10 except for 5. And this number 445 ends in a 5. So we need to put the 5-gram package on the left-hand side. And now we need, one second, I'll erase these numbers over here just for clarity. And after this, we're going to need a 440-gram package on this set, which is not going to work. So we can guarantee that E is going to be our answer with 500 on this side and a 50 and a 5 on this side. All right, let's check if we were correct. And the answer is indeed B. All right, Shelly, what about the next problem?
Cool. All right. This one was fun. I initially also thought you could only put weights on the left side, but it's cool that you could also put stuff on the right. All righty. So let's take a look at number 11. Okay. So might have to enlarge this later if you guys are having trouble. Let us know. Okay. So we have 2 identical rectangles each with an area of 18. They overlap to form a new rectangle as shown. The new rectangle can be divided into 3 identical squares, and we want to find the area of the new rectangle. All right, so let's see if we have a bigger diagram. Yes, we do. Okay, let's make this a bit bigger. All right, and so hopefully this is a bit better. Okay, so we've got 2 rectangles right here. We're given that the area of each of these rectangles is 18. So let's label with what we know. So this area is 18. We also know the area of this one is 18. All right, so knowing that, this rectangle slides over on top of this one and essentially covers half of this rectangle. And so it's kind of like split down the middle. So kind of like this, right? So if it's split down the middle, we can look at what the area is on each side. As I just saw in the chat, each of these are going to be 9 because that is half of 18. So let me write in orange the areas of the smaller rectangles. So like this, and forgive me, it's not entirely to scale. So these are both area of 9. And that means each of these squares also have an area of 9 each. And so it looks like we have 3 of these squares. So we can just add up 9 plus 9 plus 9. That is 9 times 3. That's going to give us 27, as I see some of you saying in the chat. And so let's check our answer. And it indeed is 27. Awesome. All right, I'll pass it back to you, Luke.
All right, great solution, Shelly. I really liked how you didn't actually have to find the lengths of the rectangle in that solution, which I thought was really cool. All right, so moving on to the next problem. Ooh, this looks like a very, very interesting problem. All right, so the problem reads, Rosa draws several identical rectangles to make the following picture. The width and the height of the picture are 45 centimeters and 30 centimeters respectively. And I'll just mark that off right now, just for clarity. The width is 45 centimeters and the height is 30 centimeters. All right, what is the area of one rectangle? This is very interesting. So we're told that all of these rectangles are identical, right? So that's something that's going to be very important, I believe. And the width is very interesting because the width is all made up of the length of these identical rectangles, right? So there's 5 of these lengths right here, and they make up the width, which is going to be 45. So 5 times the width, or I mean the length, sorry. So 5 times the width of all of these rectangles, the length is going to be equal to 45. So this means that the length is going to be equal to 9 because we divided by 5 for both sides. So the length is 9, and I'm going to hide the chat for a second so we can actually see this. And the length is going to be equal to 9. And this means that when we look at the height of this entire configuration over here, we have 2 lengths, one here and one here. And then we have 3 widths of these rectangles, one here, and one here. So this means that 3 times the width plus 2 times the length is going to be equal to 30, as the problem said. So now we know that 3 times the width is going to be equal to, well, this 2 times the length is equal to 18. Subtracting 18 from both sides, we get 3 times the width is equal to 12. So now we know the width is going to be equal to 4, because we divided by 3 on both sides. So now width times length is the formula for the area of a rectangle, and 4 times 9 is going to be equal to 36. And hopefully that is going to be our answer. Let's check if we were right. And yes, the answer is indeed 36. Yay. All right, Shelly, what about the next problem?
Okay, let's take a look at number 15. Right, here we go. Another geometry question. So probably we'll have to make this bigger. But let me read the question first. So here we go. The diagram shows 2 large squares with the same area, and part of each square is shaded as shown. In the first square, the midpoints of the adjacent sides are joined, and in the second square, the 4 small squares, all with side lengths equal to a third of the side length of the large square, are shaded. We're given that the area in the first square is 9, or the area shaded in the first square is 9. So we want to know the area that's shaded in the second square. All right, seems like it's still a bit blurry, so let's use this diagram right here. Okay, cool. Let's see. Okay, it's not getting bigger. There we go. Cool. Okay, so we have these 2 squares right here. So those are the diagrams that are given. And I can redraw over these in a second. So let's see, the area shaded in the first square is 9. So that means shaded is equal to 9 in this one. And so, yeah, let me redraw this because it seems like it's still a bit blurry. So this is the diagram we're given. This is our first diagram. And you can see this big outer square here. And then the corners, these corner pieces, are all shaded, right? And we're given that the points that form the new inner square, so that's this square on the inside that's not shaded, that these are joined by the midpoints of the sides. So that means if we kind of like extend out these lines right here, notice how this segment right here, right, is the exact same area as this corner piece up here. The same can be said about this piece right here, and this corner piece to its left, this one and the one below it, and this one and the one to the right. So that means that the shaded area is going to make up half of the total area of the square. And as I saw in the chat, that means the entire area of the square is going to be 18. So total, and I'm gonna call it TA, total area, actually I can write it out, total area is equal to 18. And that's not going to change with our second diagram. So let's take a look at our second diagram. So let me redraw that as well. So again, same square, so that means its area is still 18, except the shaded portions are a little bit different. So instead of connecting it by the midpoints of the sides of the square, we're splitting it up by thirds. So what that means is this section and this section and this section, there's 3 separate segments up there. So actually what we can do here is we can kind of form a grid. So if we actually connect this point over to this point to here and here and here, drawing like this middle square, so like this, we can see that actually what we're dealing with is a 3 by 3 grid. So all of these squares have the same area. So we can kind of just count what fraction of this are shaded. So it looks like 4 out of 9 of the squares are shaded. So if we multiply the total area by the fraction of the square that is shaded, then we should get the area, the actual area that's shaded. So that's going to be 18 times 4 over 9. 18 cancels with the 9. We get a 2 from that. So 2 times 4. That gets us to 8, as I see in the chat. Let's check our answer. And all right, we do get 8. Awesome, awesome. All right, Luke, what's our next question?
All right, here is our next question, and it looks very interesting. The figure below shows a honeycomb with 16 cells. Some of the cells contain honey. The number in each cell indicates how many of its neighboring cells contain honey. 2 cells are neighbors if they share a common edge. How many cells in the honeycomb contain honey? All right, let's move to a different diagram. It's going to be a little bit bigger. All right. And I'll make this a little bit bigger for you guys. 1 second. All right, here we go. I think everyone hopefully read the problem and understood what it is. Yes, I see in the chat it's like Minesweeper, and yes, it is very, very similar to Minesweeper. I will not say that I have played Minesweeper very much, so I may be at a bit of a disadvantage for this. All right, so just looking around at this, we can kind of try and see some patterns to see if we can deduce anything really easily about which cells have honey and which cells don't have honey. The first thing that pops out to me is that this 0 over here, right? This 0 over there, that means that its 2 neighboring cells don't contain honey, right? So that means that this cell over here doesn't contain honey, and this cell also doesn't contain honey. Another thing that pops out to me is this 4 over here. And since this square, this honeycomb only has 4 neighbors, this means that each of those 4 neighbors are going to have honey on it. So we'll do a circle to represent the fact that there's honey there. And these 4 neighbors are going to have honey in it. So we know already that these 4 neighbors are 4 that have honey in it. All right. Looking at some more things that we can try and deduce, this 2 over here is going to mean that, this 1 right here only has 1 neighbor that contains honey, and that neighbor is already right there. So that means that the 3 does not contain honey. Let's see if there's some other things that we can do. This 3 right here has 4 neighbors, and 1 of them doesn't contain honey. So we can say that the 3 right here does contain honey. Let's see here. This looks very interesting. I don't know if there's anything we can deduce immediately right now. So maybe we could go off of hypotheticals. Oh, look, there's a 3 right here, and there's 4 neighbors for this honeycomb. So that means that because of this one x right here, its 2 other neighbors are also going to contain honey. And this is going to hopefully let us finish it, I think. From this 4 right here, 4 of its neighbors already contain honey. So its 2 other neighboring squares are not going to contain honey. We can cross out these 2. They definitely don't contain honey. This 2 right here, we know that this 3 right here and this 2 right here don't contain honey. So this 4 is going to have to contain honey. And from this 3 right here, these 3 neighbors contain honey. And so that means that this 3 down here does not contain honey. And, oh, I could have done this a long time ago. This 1 right here has 1 neighbor that contains honey. So this 3 and this 4 do not contain honey. And we just have 1 more left to go. This 1 right here does contain honey because this 2 has 1 neighbor here who that does contain honey. And these 2 neighbors do not contain honey. So we're going to circle this. And I think there are a lot of different ways you could have filled that out. It's not necessarily that difficult to find a lot of different paths to do that, but this is kind of the path that I chose. And so now we look back at the question to remember exactly what we were asked. And the question is, how many cells in the honeycomb contain honey? All right, let's go back to our diagram and count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 9 honeycombs, and that's going to be answer choice C. All right, let's check if we were correct. Yay, the answer is C indeed, and we succeeded in Minesweeper. All right, Shelly, what's the next problem?
All right, cool. I do have to say, I think this is one of my favorite questions so far because, like, you look at this and you're like, what is going on? Unless if you play Minesweeper, right? This is very similar to that. But I personally haven't. So yeah, this one's really cool because there's like so much information that you can get out of it almost. Also feeling like there's no information. But yeah, if we just start from here, kind of take any path. That's cool. Okay, let's take a look at 19. I anticipate having to make this bigger too. So let's take a look at the question first. So Christian has cut 4 small squares from the corners of a larger square so that the remaining area is half the area of the original square. The side lengths of the small squares are shown in the diagram. So what is the perimeter of the remaining shape? Okay, so let's take a look at what we've got here. So, all right, let's get this diagram going. So, let's make this bigger. Cool. Okay, so we're dealing with this square right here. And yes, let's get the side lengths going. So we don't actually know the side length of the large square currently, but what we do know is this. So we have this large square. Let me trace it out. And we know that there's 4 corners that are being cut out of it. So this square over here has a side length of 2. And then this right here, this corner, has a square of side length of 3. This one's a little bigger, and it has a side length of 6. And then at the bottom left, we have a corner of 1. Right, so hopefully that's a little clearer. So let's see, what other information are we given? What haven't we used yet? Well, we haven't used the fact that the shaded or the parts that are cut out are half of the area of this larger square. So let's see what the area is. So this square right here is a 6 by 6. So 6 times 6 gets us an area of 36. We have a 1 by 1. So that area is going to be 1. 2 by 2 up here is going to get us 4. That's from 2 times 2. And finally, this corner, we have 3 times 3. It's going to get us 9. All right. So, as I say in the chat, 36 plus 9 plus 4 plus 1, that's going to give us 50. So 50 is cut out. And so that means the total area of the entire square is going to be 50 times 2. That's going to be equal to 100. So total area is going to be 100. What does this tell us about the side length of the large square? Well, the large square is going to have a side length of whatever the square root of 100 is, because we have side length times side length is equal to 100. The square root both sides gets us the side length as 10. So side length is going to be 10. So this entire length over here. All right. And now we want to find the area, or not the area, the perimeter of the shape after all of these corners have been cut out. So that looks like it's going to be this border that I'm drawing in yellow. So it's essentially the square, but with the corners cut out. Okay, that seems a little bit of a pain, just because we don't really know like these lengths. We can certainly find them. There's a nice trick to this though. So what we can actually do here is we can move these lengths around. And let me show you what I mean. So this length, for example, what if I move this one, this length up here, take it out to over here so that it's bordering the bigger square? What if I take this segment over here and then drag it out to this segment out here? Well, actually, that's actually really convenient, right? Because this length and this length are the same because they're all part of the same square. So that means if we just move the segments around, actually, I'm going to do it in orange. So if we move this segment out over here to the orange segment, these are still the same. And same with these ones. So if we move this one out over here, instead of calculating this corner right here, we've essentially kind of like flipped the corner on the outside. So the length of this inner portion is the same as this outer portion. If we do that for the rest of this, like moving this segment out over here, right, and as I just saw in the chat, you can move all of the corners. That's what's really nice about this, actually. So we can move all of the corners. And essentially, instead of finding all of those segments like individually, which could have taken a lot more time, we can actually just find the perimeter of this entire square, right? That's the perimeter of this entire square is what we're trying to find. So we know the side length of one of the sides, or we know the side length, right? So the perimeter of the square is going to be that times 4. As I see in the chat, that's going to be 40 as our perimeter. All right, let's see if we're right. Cool, and it is 40. Awesome. So very nice process. I'll pass it on to Luke now.
Yeah, really, really good solution. I will say I didn't necessarily find the nice solution and went through all the terrible arithmetic without just popping out those squares as you geniusly did. All right, next on to the next problem. And this is problem 21. And it looks very interesting and it's like 3D figuring. All right. There are 3 identical special die on the table. What is the sum of the numbers on the faces that touch the table? All right, this is very interesting, and I've never really been that good at 3D figuring, so we'll see how this goes. All right, let's start with the first die, and we'll just try and figure out which number is going to be on the bottom for each of the die based on the positions of the other die. So we're told that it's the identical die, right? And the first thing I notice is that the number is going to be the number below the number 8. And so if we kind of think about it, if we look at the second die, we have 13 under 8. And this 8, if we kind of rotate it, we rotate it in such a way that this 8 is going to be on the side. If this 8 is going to be on the side, then that means that the 13 is going to be on the bottom. So in the first die, the 13 is going to be on the bottom. And that's 1/3 of our problem. All right, next we have the second die. And something I noticed is that the third die tells us a lot about this situation. And so if we kind of do a very, very similar thing to what we did in the last problem, we have the 13 over here and next to the 22. And so this 22, if we kind of rotate this die, we're going to have the 13 on this side, precisely where it is in the picture. We're going to have it right there. And then we're going to have the 22 on the bottom. So that was very, very similar to our first, the way we found 13 on the bottom. All right, now for our last one. Now, in a very, very similar to how we did the last two, if we have 22 on this side, then, and we look at the first die, we have 22 right here and 8 on this side. So if we kind of twist it around, we're going to have 22 on this side right here and 8 on the bottom. So if we add up all of these numbers, we're going to get 13 plus 22 plus 8 is equal to 43. And hopefully that's going to be our answer. And we check, and the answer is indeed 43. Yay. All right. Shelly, what's the next problem all about?
All right, terrific. Let's take a look at 23. Okay, let's see what we've got. So, train problem. Okay, so looks like the figure shows the plan of the 7 train routes of a small town. The circles indicate the stations, and Martin is trying to paint the lines in such a way that if the 2 lines share a common station, then they are painted with different colors. So what is the smallest number of colors that he can use? Okay, well, let's try it out and see what happens. Let's see if there's a diagram for this. Epic. Okay, well, we have this diagram over here. And hopefully it's not too blurry. Let's take a look here. So let's just try some combinations and see what happens. So what immediately draws my eye is these 3 parallel lines right here. So these parallel lines are never going to cross each other. That's what parallel means. So at least in this diagram. So let's paint all of these the same color and see what happens. Because we're trying to reduce the number of colors used. So we want to be able to paint as many lines as one color as possible. Now, if we can't avoid but to use another color, then we're going to have to, right? So it looks like we have these 3 painted. I'm painted the blue. You could do any other color. And it looks like, well, all of these other lines are going to cross a blue line at least one time. So unfortunately, we've run out of lines that we can use blue for. So we're going to have to use a second color. Let's do, I don't know, let's say like yellow. And going off of the parallel colors here, I see these 2 over here. These 2 are also parallel to each other, so they're not going to cross over. So let's do yellow for these guys. So right here and right here. Okay, and then with these guys, the 2 that are left, oh, well, they cross both the blue and the yellow ones. So we're going to have to use a third color. I'm going to pull out orange. Okay, well, let's see. This one, the crosses right here. Oh dear, my line has gotten out of whack. Okay, so like this, right? And fortunately for us, this other line doesn't cross this orange one at all. So we can still use orange right here. And it looks like in total, we've used 3 colors. So let's take a look back at our answer choices. Well, it looks like 3 is the smallest number that's given to us anyway. So we don't really have to worry about like, oh, do we actually get the smallest number? Because we already did. So let's go with 3, see what happens. And it indeed is 3. All right, awesome. Okay, cool. Luke, what's our next question?
Yeah, really, really good solution. I liked how you used the fact about the answer choices and how 3 was the minimum. So we knew we got our answer. All right, next problem is problem 25. And this looks very, very interesting. Simon takes 4 cups out of the cupboard and puts them randomly on the 4 saucers. For each cup, there is exactly 1 matching saucer. Which statement is correct? All right, so I think I'm just going to approach this problem by reading the 5 answer choices because we can't really say anything about this until we read all of the answer choices. So 4 of these statements are going to be incorrect and 1 is going to be correct. So we'll just go through each of them and see which one of them we can make happen and which one of them we can't make happen. All right, let's look at the first one. It is certain that none of the 4 cups stands on its matching saucer. Well, I don't think that's necessarily true. Let's say that these 4 saucers are named A, B, C, and D. And then their matching cups are just going to be A, B, C, and D as well. So for example, we could just put cup A on its saucer, and then we can arrange any of the other 3 cups in any way we want, right? And that's just going to guarantee that one of the cups is going to be on its matching saucer. All right, let's look at the next question and see if this is possible. It is certain that exactly one cup stands on its matching saucer. Well, I see a very, very easy counterexample to this. If each of the cups is on its matching saucer, if A is on D, if we have A over here, if we have B on its matching saucer, which would be A, if we have C on its matching saucer, which would be C, and if we have D on its matching saucer, which would be B, this is going to be a counterexample to this argument. All right, the next answer choice is, it is impossible for exactly two cups to stand on their matching saucers. All right, let's have saucer A right here, saucer B right here, saucer C right here, and saucer D right here. And I know it's a little bit confusing with the names of the saucers and the names of the cups because they don't exactly match up. But let's say we had saucer A. Oh, let's say we had saucer B on saucer A. These two match together. And now we'll choose just the first two to match up exactly. Then let's just say we had saucer D on saucer B. These two match up exactly as well. And for saucer C, we don't want it to match up exactly. So let's put saucer A on saucer C. I mean, cup A on saucer C. And then finally, we'll put saucer C on saucer D. So these two don't match up. These two don't match up. But this pair matches up, as well as this pair matches up. So we know the answer is not going to be A, nor is it going to be B, nor is it going to be C. And if we actually skip ahead and look at answer choice E, it says it is impossible for all four cups to stand on their matching saucers. Then we know that this is not possible either because we just had a counterexample over here. So we know that the answer choice is going to be D. And now I'll try and explain why we can't have what number D says. All right, it is impossible for exactly three cups to stand on their matching saucers. So let's say we had A with B, B with D, and these are going to be matching, and C with C. Then the only choice we're left with for the last cup and the last saucer are going to be D and A. And this is not going to work because these are going to match. And this is always going to happen because if you think about it, if you have three saucers that match up with three of the cups and you match them together, the only pair that's going to be left is going to be one saucer and one cup that already matches together. So this is not going to work. So now we know that the process of elimination and actually testing the answer choice, that the answer is going to be D. And so I can be pretty certain that this answer is correct. All right, now if we check our answer, and the answer is indeed D. All right, Shelly, what's the next problem?
All right, awesome. Really loved how you used the process of elimination here. That really helps in narrowing down this question. And let's take a look at number 27. This is another one of the long ones. So let's make this a bit bigger. So our question over here, well, we don't have a diagram, so it's just words. Okay, so a grandmother has some candy. She decides to divide it among her grandchildren so that each has a bag containing the same number of pieces of candy. She puts the largest possible number of pieces of candy in each bag. And when she's done, there are 20 pieces of candy in each bag and 12 are left over. So what is the smallest number of pieces of candy that she can have? Okay, seems like we are not given that much information here. The only pieces of information that we're given is that there's 20 pieces of candy in each bag. We don't know how many bags there are, so I'm just going to draw like arbitrary looking bags and with dots because we don't know how many there are. So each of these we know has 20 candies. Okay, and we know also that 12 of them are left over. So that means the 12 candies were not able to be distributed evenly throughout. So we know that the number of bags that are there cannot be a factor of 12. For example, it can't be like 1 because all of the 12 candies are just going to go in that one bag, right? And so an observation I just saw in the chat is the number of bags has to be greater than 12. The reason why that is suppose that we don't have the number of bags greater than 12. Let's say we have like 8 or something like that. Well, if there were 8 bags, then we can still give one more piece of candy to each of the kids because we have enough, right? We would have, like, say, 4 candies instead of 12. So that means, like, with any value less than 12, we can kind of still split candies around. And so that means the number of bags has to be greater than that. So the next possible option is 13. 13 works because now one of the kids at least is not going to get the candy, right? You can give one candy to 12 of the kids, but the 13th kid is going to be really sad that he doesn't have that piece of candy. So that means 13 could work in this situation. We have 13 bags, and we don't want it to be any bigger because we're trying to look for the smallest possible number of pieces of candy. So let's do 13 bags times 20 pieces of candy in each of those bags, and we still have those 12 pieces left over. So our total number of candies is going to be 13 times 20, that is 260, plus 12, that's going to give us 272. So I'm seeing in the chat C. All right, let's see if that is the right answer. And indeed it is. All right, awesome. Okay, I'll pass it on to you, Luke, for our last question, I think.
Yeah, really, really good solution. All right, so problem 29 and the last question of this live solve. And it looks pretty difficult. All right, the question goes like this. Emma is playing with the 7 caterpillar puzzle pieces shown. She wants to build a caterpillar that has 1 head, 1 tail, and 1, 2, or 3 puzzle pieces in between. How many different caterpillars can Emma build? All right, some key things that I'm just going to highlight is that we notice that it has 1 head and 1 tail. All right, so let's kind of look at our pieces now. I noticed that 2 of these pieces have rounded off edges at the top, which mean that those 2 could be the head, right? I'll circle the other one that I did not circle. And 2 other pieces could be the tail that have the rounded off edge on the other side. So these 2 could be the tail. So for every caterpillar, we're going to have 2 options for the head and 2 options for the tail. One other thing that I notice is that these 2 for the head have the same connection thingy over here. I don't know exactly what to call it, but connection thingy over here. And so these 2 can only be connected to this piece, actually, because if we look at all of the other pieces, none of them have this same connection thing as this one does. So this is the only piece that can be connected to this head. All right. Another thing I noticed is that these 2 tails have the same connection over here. And these 2 are going to have to be connected to either, balloons. They're going to have to either be connected to this puzzle piece right here, or this puzzle piece right here, or this puzzle piece right here. So that actually doesn't give us that much information. All right, let's go ahead with this problem. And one other piece of information I want to bring to our attention is 1, 2, or 3 puzzle pieces. So I think we can make casework based off of that information. Let's say we have case 1, where we have just 1 puzzle piece in between the head and the tail. And we'll kind of name our cases based on the number of puzzle pieces in between. So that kind of makes sense. All right, we have 2 options for the head and 2 options for the tail, as I said before. And these are going to be the same because they have the same endings and the same beginnings, I guess you could call them. All right, now, as I said earlier, this is the only piece that can be connected to these 2. So we actually only have 1 option for the 1 piece that is going to be in the middle. And it does indeed work because this ending on the left-hand side does work with these pieces. So we have 2 times 2 times 1 for case 1, which is going to equal to 4. All right, now we have case 2, where we have 2 pieces in between. All right, so we could have one of these 2 heads and one of these 2 tails. So we're going to multiply 2 by 2. And then we have to figure out the number of ways to fill in this middle. All right, in order to fill in this middle, we have to choose this piece to go to the farthest right. And I'll letter them out here because it's going to be getting a little confusing. So let's say we have A, B, C, D, E. Ooh, that was a bad E. E, F, and G. All right, so we either choose F or G for the head, A or B for the tail, and then we're going to have to choose D. Let's just say we chose F and B, all right, for the head and the tail. I'll give a sample run over here. Now, as I said earlier, for the one next to the head, we're always going to have to choose D because it's the only one that works with this ending and this beginning over here. All right. And then for the next option, we could either choose C or E. So we could either choose C or E. Either of these work. And then we also have, as I mentioned earlier, 2 options for the tail, 2 options for the head, times 2 options for that second piece in the caterpillar. This is going to be 2 times 2 times 2 is equal to 8. All right, we just have one more case to go, and this could be the hardest one potentially. Case 3. We're going to have 2 options for the head and 2 options for the tail, just like we've had every single time. All right, now this time we're going to have to include all 3 of these pieces, right? We're going to have to include D, C, and E. So that's interesting. Let's just say, as we did earlier, that we had hypothetically B for the tail and F for the head. We could have chosen G or A for either the head or tail respectively, but we chose the ones we did. And as previously, we're going to have D next to the head. And then we can put C or E in either order here. And the reason why this is because these pieces are exactly the same, and they're going to have the same endings that are going to work with D, or with B or A, or with each other, actually. So we could either have CE or EC. So that's 2 different options. So 2 times 2 times 2 is equal to 8. And when we sum all of these up, we get 20. So we'll circle that for our answer, and now we'll see if that is correct. Yay, the answer is indeed 20. And that is the last problem for today. So it's 8:01. So thank you guys so much for coming. It was a lot of fun teaching you guys. And Shelly, do you have anything else you want to add?
Not really. Just thank you guys for coming. I hope you guys had a lot of fun here, especially with participating in the chat. It's all really good participation. And also, if you want to see this later, it's also up on the YouTube channel. So there is a live by Po-Shen Loh channel, and it'll be posted there. So if you're in the live stream, you already know where that is. It'll just be up there later. If you're from the Zoom, you can check out that YouTube channel. It's got some other bits and pieces as well. We've done like AMC stuff. We've also done other Math Kangaroo stuff if you're interested in those. But yeah, thank you guys for coming. We hope to see you at another session. Bye, everyone.
Bye, everyone. Thank you guys so much for coming. It was a lot of fun.
Yes, thank you. Bye-bye.